In designing a circuit board, you have to take into so many considerations to end up with something that actually works. It's like a miracle every time. Thanks for laughing. So I'm going to try and run through some basics, okay? And if anyone wants to dive into something deeper, please tell me. And if I have more to say on the subject, I would do that. But basically, when you think about PCB design, always start with your stack up first. How many people have designed stack ups that are more than one lamination? Okay. So how did that go? Yeah, more than one lamination causes so many more complications in fabrication. So hopefully I can touch on some of those. You have to pick your PCB materials not just for electrical properties, but also for manufacturability. So that's like the first kind of thing. Then you get your stack up, and then you have to actually lay out your board. Forget components for a second, selecting components. So you have to lay out your board in a way that is etchable. And then balance all of that with, hey, does this thing perform electrically? Because really all a fabricator and an assembler is responsible for is to make sure that it meets a spec. And that's it. Not really that it works for you, but that we've manufactured to a spec. That's literally the thought process of a fabricator. So there's just a lot going on in there. So DFM is a thing, and it's very important because for a couple of reasons. First is you'll be as close to having something that works at the end of the process. Number two, if that board is ever going into anything serious or going into production, you'll be passing on something nice rather than a nightmare. Just a quick story. We're building a military board right now that was designed 10 years ago. And that board, that design literally is bouncing around from PCB shop to PCB shop because no one wants to make that board because it's impossible to build. It's not that difficult. It's impossible to build, but the scrap is so high that no board shop wants to make it. Somehow we got stuck holding that bag. And so we're building it, but literally every single month we raise the price because we can't lose money on it, right? Otherwise, why would we want to build it? And that customer keeps sending us an updated PO with an increased price because they have no choice. So this is, you want to avoid that at all costs, right? It's like, do good for the world and don't design something without going through a DFM process. So that's what this is about. Is that motivation? Was that story motivating? By the way, I invite anyone to come and, tour our factory and run one piece of equipment one time without getting your fingers chopped off. Okay, so when you pick your PCB materials, if you guys haven't heard, you need to really think about what the dielectric and core materials are when selecting that material. How many people know what a core material is? Okay. You guys probably know more than I do, but I'm up here. So if you have a specialty material like high-speed materials like a Megtron or EMCs becoming popular, any kind of high-speed PCB material, it's really important to make sure that your fabricator either stocks that material or you communicate ahead of time and they order ahead of time because material delays happen. It's a practical part of the business, and a prototype that is waiting on PCB material is not really a prototype anymore. And I have a lot of customers that aren't really happy about that, but if we don't have the material, we don't have the material, right? So pick materials and cores that your fabricator possibly has in stock, and you would have to know the core materials, especially in any high-speed designs. You want to work out that stack up ahead of time. So, one point in terms of a DFM is you want to make sure that the materials you pick are appropriate to your design specifically. And one of the things that a manufacturer has to consider, and the designer should also, is there enough, let's say, pre-preg to melt during lamination to properly bond your copper layers together? And I know it's a little nuanced, but a class 3 board requires 2 plies of pre-preg in between copper cores for just that reason, because you don't want to end up with a board that has voids in the materials or any potential of separating, which is called delamination. So that means that even after the board fabricator has built a good board and checked that there's no issues, that you could still have delamination after the board is in the field, which is the worst case scenario. So you want to make sure that you picked a material that flows properly for your design. And really what that means is that if you have a board that has a nuance, your fabricator is going to find out about it and really give that feedback to you. And that is the point of prototyping, right? Don't just throw it over the wall and expect version 1 to be perfect. So going back to the nightmare I was describing, that designer designed a very large board with a very uneven copper distribution on the cores. So core is, again, copper on both sides. One part of the core was, 2 ounce of copper, flooded ground basically, and the other side was very long, parallel 3 mil traces, and that makes etching very hard. It makes all sorts of kind of imbalances in the construction, and hence why very few American fabricators can build it, and lots of scrap. And they can't change the design because it's ITAR and military and 10 years old and all of that. So I kind of talked about those. This is a video of a highly paid blue-collar worker that is basically putting together what's called a book, putting together the cores, putting together the pre-pregs, and then, per the modeling, and then putting it into a lamination press. How many people have seen a lamination press? Ooh, less people. I again invite you guys to come. But this is a lamination press. We have oil lamination presses to apply heat evenly across the sheet. Because if you don't apply heat evenly, then some places will melt more, some places will melt less, and then you have the delam issue that I was talking about, or any kind of voiding you might have. So that's what lamination is. The next kind of thing to think about in DFM is copper etching. I alluded to having very thin traces on one side and very thick amount of copper pour on the other side is very hard to etch. The other thing that's hard to etch is when you have heavy copper. You end up with these trapezoidal features. You end up with areas where you can't etch out to properly, have a nice clearance. And this is where the designer really plays a big role. If the designer can add enough spacing where they need to, then even if you have a little bit more copper, like a 2 ounce or 3 ounce, the manufacturer won't have any problem etching out the copper that they need to. So knowing which cores you're using, what the copper weight is, and what is the spacing that you can design to so your fabricator will really not have any problems. Does that make sense? Spacing? Yeah. So this is not trace-to-trace spacing necessarily. This is also basically any copper features. So if you have like a trace next to a ground pour, what's the spacing there? It should be at least 10 mils of spacing, and then if you have heavy copper, it should be more. So here are some very common etching issues. First one is the uneven copper distribution, which I was talking about. So one thing I really like in the new KiCad is the way you can control your zones, and you can, really kind of more automatedly, pour your copper, which is great. And then if you want to move some traces around, you can then re-pour your copper. If anything that a PCB design tool can make it easier to pour copper properly with enough spacing per your DRC rules, you're going to get a better electrically performing board, and it's going to be easier for your fabricator to etch. And then also in lamination, things will stick together. So all that, you get all of that with a nice copper pour. And I didn't even mention, electrical, better return paths and, less EMI issues to deal with later when your design's done. So all that is because of copper pour. So how many people use copper pour efficiently? That's good. Preaching to the choir. It's good. All right. So the other issue that can happen is sliver formation. So it might be hard to see, but if you look up where there's arrows, you don't want like this little bit of leftover resist in our etching process, because that can flake off during plating or etching, causing all sorts of problems. So be careful of not having inadvertently designed in any slivers. And the other item here is basically, how you really, kind of keep copper from the edge of the board and not have any exposed copper after someone's done routing your board. The next big area is designing your via structures. So a few of you had mentioned, or a lot of you had mentioned, that you've done boards with multiple laminations. So it looks like in KiCad 9, you really have a lot of leeway on designing your different pad stacks and drills that go from one layer to the next. Maybe they're blind vias that are really tiny. Maybe they're mechanical subs, mechanical drills for your subs. These all have different design rules for annular ring and different design rules for aspect ratio. So all super important. So it looks like KiCad 9 really supports that well. So for a mechanical drill, even though the mechanical drills are getting really good and are very accurate, almost as accurate as laser machines, people still want, fabricators still want larger pad sizes for your mechanical drills. So you should aim for a designed in annular ring of as big as possible. So maybe 7, and if you can't do 7, a 7 mil designed annular ring, then 6, then 5, then 4, then maybe your fabricator might say, sorry, that's a little bit too much now. You should never push your fabricator. So the other option, the other thing to consider is aspect ratio. So if you have a sub, like a 4-layer sub or a final through-hole drill, mechanical drill, we're plating the sub separately. We're plating the final through-hole mechanical drill separately. So in those scenarios, you want to make sure the aspect ratio is right for that plating process. Also recognize that when you're plating a sub, that inner layer can be considered an outer layer. And so you're not processing an inner layer, you're processing an outer layer. And there's different design rules for outer layers versus inner layers. Okay, so also for drills, other than aspect ratio, annular rings, pad sizes, is drill to copper. Drill to copper is a little bit tricky because the way that we like and most fabricators like to see the finished files is to see a finished hole size plus or minus a tolerance. And then most manufacturers will drill larger than what you specify as the finished hole size. And in that case, when you're drilling larger, you could have that drilled hole wall too close to another copper feature, maybe a ground pour that I was referring to earlier. And if that clearance is not at least 8 mils, then most fabricators would have a problem. And the reason why fabricators would have a problem is that PCB materials move around a lot, and they especially move around after lamination. And that's called misregistration or registration issues. So every fabricator has to deal with how to realign drills after lamination before plating. And so most fabricators are looking at the data, trying to figure out the scaling, and then they'll drill. But if you don't leave enough spacing from a drilled hole wall to the next copper feature, if it moves around a little bit and the drill wanders during drilling, all these can happen. You could end up with a board that is quasi-reliable. Again, maybe it went through testing, everything's good, but then when it gets into the field, you have field failures because of a problem like calving or any other kind of vibration or expansion and contraction. These are all real issues that can happen. So having a board that's functioning after manufacturing is not still necessarily a reliable board. How many people design for aerospace? A couple people. So in aerospace boards and Class 3A boards, you have a wicking requirement, and wicking is essentially the acknowledgement that after a board is built, even though it's good and electrically performs, you can have field failures with copper, migrating and wicking through the materials of the PCB. So it's a real issue that has happened and plagued the industry. That's why you have different requirements for flight boards than Class 2 boards. How many people work for SpaceX? Okay, good. I can say something bad about SpaceX. So SpaceX literally has been designing to Class 2 boards and then wondering why stuff doesn't work. I recommend that you follow IPC class specifications. You will get a more reliable board. I know it's a groundbreaking suggestion, but I'm not cheap. I don't know. Okay, so enough about drilling. We talked a little bit about annular ring. Another thing that KiCad offers is teardropping. So teardropping is great because it gives you a little bit more leeway as a fabricator if the drill doesn't hit directly into the center of the pad, or because of scaling, the drill needs to be offset a little bit to basically find the best center across all your layers. You have a teardrop, and so that kind of helps a little bit with, not having to scrap a board and restart. And obviously, I'm talking about designs that are a little bit more complicated, a little bit tighter. But teardropping is great practice, no matter what kind of a design you're doing. So what the picture you see on the slide is breakout, and breakout does give you a decent electrical connection. But for Class 3, it's not okay at all, and for Class 2, it's okay, but people probably don't like to see that. But it's fine for Class 2. That's why you don't want to put that in space. This is just a quick video of laser drill. So laser drill is great because it has really good registration, and of course a laser drilled hole can be very tiny. Down to 3 mils is what we consider is pretty much standard. However, it really just goes from one layer to the next. So if you have a laser drill from 1 to 2, that's still only one lamination, so it's not going to really increase your cost very much. But if you start having laser drills from 1 to 2 and then an offset laser drill from layer 2 to 3, that's basically 2 laminations at least. And every time you have a lamination, it's basically going through the manufacturing facility twice, and that really does increase cost and lead time, and it's not conducive for quick cycle time. So you can definitely get benefit for laser drill. You can even get cost reduction with laser drill, but you have to really think about it and plan your stack up ahead of time. I dedicate this slide to solder mask. I don't think solder mask gets enough attention. Does anyone have any assembly issues ever? It might not be because of the assembler. It might be because of the solder mask design. Seriously. Because we assemble also, my assembly shop is always blaming our fabrication shop for poor solder mask. But sometimes, it is the assembly. It is our own assembly shop. But be aware of your solder mask. So solder mask web, I think, is the key thing. Most fabricators that don't also assemble, they would ask for, if there's not enough solder mask web between the pads, they would ask you to remove that web, and that's called like a gang opening or a window. Well, that's very easy to fabricate, but very hard to assemble now, because the purpose of solder mask is to prevent solder from, bridging and things like that. So they just completely eliminated the purpose of solder mask. So yeah, so we don't ask for asking for windows anymore in the solder mask. Instead, we ask to maybe add a little bit more webbing, encroach the opening onto the pad a little bit. That's also okay. And just get a bigger web. So we like a 4 mil web. I think most fabricators are down to 3 mils. We're special that way. And if you have anything other than green, definitely have a bigger web, because these other colors, even though they look really nice and pretty, they're hard to expose. They're hard to process. They have a different processing window than green. So you want to design to a different color of solder mask. Did everyone know that already? Oh, I got someone who didn't know that. That's good. I'm going to pat myself on the back. All right, it was all worth it. Yeah, different colors process differently. So, and if you're going to have like a tight, dense design, probably just go with green, or really ask your fabricator what their tolerances are for the web. Silkscreen also deserves a shout out. There's a lot of designers who make their silkscreen kind of impossible to read. AOI at assembly does use silkscreen. Did I say solder mask? Does use silkscreen to look for pin ones and to make sure the components are rotated properly and to make sure it's putting the right component in the right spot. So silkscreen is still definitely useful in assembly. So try and design your silkscreen so it doesn't get clipped away by the fabricator, because there is no. It shouldn't be allowed to have silkscreen on top of a pad. That would also be a problem. So just be aware of your silkscreen, that you're following the guidelines for that. So just a couple of sentences about what you should do before you send your design to a fabricator. I'm really encouraged by all the power in KiCad. Being able to set up custom DRCs, being able to set DRCs per layer. So if you have like a core layer that has 2-ounce copper, you can set spacing guidelines differently from, let's say, other signal layers that have 1-ounce copper or half-ounce copper. These are really powerful features, and KiCad is making that available to you. Absolutely set as many DRCs as you possibly can. That will help you later on, when you're about to throw the files over to the fabricator. The second thing is KiCad supports ODB and IPC. I know people love Gerber. I would never use Gerber. I know that's hurtful, right? Well, if you do ODB or IPC 2581, you can kind of visually check it and make sure it is what you designed. Gerber is, I would say, just old. And it has no information. It's basically, you have to send all these other informations with it because it doesn't have anything. And for an assembler, it's almost impossible to assemble with Gerber. You have to recreate ODB or 2581 to assemble your boards. So if you're going to send, files to us where we do fab and assembly, we basically need ODB or IPC 2581. And KiCad has you covered on both those formats. So I think it's a no-brainer for that. Second, you want to verify early on that you have picked components that are readily available and you have a well-formed BOM. Even though COVID is like kind of, we're over the worst of it, there's still supply chain disruptions. There's still delays in components. I don't know why. Maybe you can ask Corvo. But we experience it day in and day out. Even if DigiKey says they have it, maybe they don't the next day. All this type of stuff happens. So if you can pick a component that's readily available or that your assembler has on their shelves, all the better. So these are a couple of things you can do ahead of time to make sure that your order goes really well. And, lastly, fab notes. Where's my, I thought I had fab notes in here. But make sure your fab notes really call out anything, special. Maybe you have edge-plated holes. Maybe you have tolerances on your cutout. Maybe you don't want any contamination in a certain area. You're very sensitive to a certain area of the board. Anything special at all, that's what fab notes are for. you can copy fab notes. Please don't tell anyone I said that. You can copy fab notes, but read them before you send them to us. Yeah, fab notes are important. We read them. If we don't, we get in trouble. So you should read them too. This is some of our, our overall kind of like, hey, what do we check for at each stage for DFM? We have a really nice DFM guide that's out on our table where Lucy is manning. She's a very wonderful lady. You can talk to her. She's out there. She lugged all these crazy design guides, which have great information. So I am pitching you not to buy a circuit board, but just to pick up a design guide and say hello to Lucy. And with that, I think I'm over. I'm done. Thank you.
I am so happy you brought up fab notes.
Thanks.
Well, I actually know because I've been through every possible iteration of every way of doing it through different companies, and I always want to understand the perspective from the other side. When you're a hobbyist, you don't even know those things exist. When you're building things and there's money on the line, they're important. Like, for example, Altium has a tool called Draftsman, which is beautiful. You can make a readme.txt. I've been trying, and I redo the workflow, it seems like every year, about how to standardize so my process is quick, but also so it's quick for the person on the other side. And maybe you could comment, what would people like you want to expect, or are there standards? I would love it if the IPC file could just bake it in, because it's like such an important thing. So yeah, so I'd just love to hear your thought on that.
Oh, I think that's an amazing idea, because we get fab notes that make no sense. We get fab notes like fab note number 7 says one thing, fab note number 12 says the exact opposite. It's just kind of all over the map, and people do what they want. And I think that's an amazing idea, frankly. And you should join an IPC consortium just for that. It might suck up some time, but.
Well, I think where I'm is one thing I'm passionate about it when I'm looking at KiCad. You can certainly do it in the PCB doc and the schematic of. Sometimes it's figuring out a way that you can minimize time and get maximum value, and everything from where's pin 1 on that LED and just where should conformal coding go, and so the outputs are nice and clean, and you can get the happy button, as I call it, just to generate docs, because I'm guessing you receive them in on carrier pigeon, smoke signals, whatever. So
it happens.
Yeah.
Yeah, we got a CD the other day. I was like, what?
What?
Something that Sierra has done, and we're very open with information, and on our website we have a knowledge base section, and it lists out what the fab note should look like, at least what the bare minimum information. So if you're designing edge plating, or if you're designing, conformal coding, or whatever special feature you may have, what would the fab note look like? And honestly, one of the number one things is, what are the surface finish specs that you should call out? Like, some people still, ask for 100 microinches of soft bondable gold, which is going to cost them a fortune, and where it's sometimes not needed, or ENIG that's, there's too much gold, even per IPC, that they're calling out. So we've put all those basic fab notes there on our knowledge base. We also just recently put together a checklist for designers that we'll make available. That's what we've done. I think there's other questions.
So along a similar train of thought, precisely speaking, where in what form do you prefer to have the fab notes? You just want a PDF thrown in with the rest of the design files? Here's a zip and here's a PDF of my Word doc of me typing things out. Is there what is, I understand you can do a lot of things, but what is most digestible for you, the fab house? Yeah,
I think having at least one layer in your design that is basically a fabrication drawing, and then also outputting that into PDF as well. Okay. Because our obviously we can view data. That's not an issue, but, it's also very convenient to have it in PDF. So anyone on the shop floor can pull it up and things like that. So I think having your fab drawing as a layer, as well as, a PDF is just perfect. It's fine.
And by a PDF, you mean a PDF of just that layer?
Yeah, exactly.
Okay, cool. Thank you.
Yeah.
Thank you.
Yeah, great question. Well, if you have a fab drawing and an assembly drawing, that's already like huge. I know I have low expectations, right?
So back here.
Sure.
Recently worked on a board where we had these little QFN parts with an exposed pad in the middle that were having some solder connectivity issues. You mentioned mask, but it turns out the issue for manufacturing on this part was the stencil.
The stencil, yeah.
It turns out they had the area in the stencil for the exposed pad was a little too big. They put a little too much solder in the middle, and so it raised the middle, and all the edges were little columns, and a couple of them disconnected. And so the fix was smaller, like quadrants in the solder. Do you have any suggestions about solder masks and anything that KiCad might do to help with solder mask, or not solder mask, stencils?
Solder paste. Yeah, that's called the solder paste layer. Again, I'm not a PCB designer, but when you're designing a component, I know you design the solder mask part of the component, right? When you're doing a component library, do you do solder paste also, or can you? So, I think Sierra should contribute to that. I don't know how, but, we are continuously refining solder paste design, because what the notes that come out of the semiconductor company is not always the ideal notes for fabrication. They may say the mask should look like this, they may say the paste should look like that, but it's not really sometimes actually the best. And so we have all this real world knowledge on what solder paste should look like, and we basically make mistakes too. So in our assembly facility, we have a solder paste deposition machine and then a solder paste inspection machine, and we just replaced the solder paste inspection machines with newer machines, better machines. And it's really about collecting the data and making sure that the solder paste is the right volume. So yeah, that was a really good feedback you gave. Yeah, it's really nice.
Do you still need fiducials for parts placements?
Who's speaking? I'm sorry. Okay.
Yeah. Do you
yeah,
still
no,
need?
it's on.
Yeah. Do you still need fiducials on the board for part placement?
Yes, definitely. Fiducials are really important. The equipment's always getting better. Equipment's always getting more accurate. But if your board is getting denser and you're putting down a tight pitch component or a sensitive component, to placement, having a localized fiducial is really key to part placement. Because I remember going back to PCBs, I mentioned PCB materials move around. The boards shrink or stretch during processing and after lamination. And prior to assembly, pick and place and solder paste, our assembly shop is using our scaled data from our fab shop and, to get as accurately as possible, to get the stencils designed properly and put the paste properly, and then pick and place also to be more accurate. And I think that's a really key thing. And, this literally happened. I had a customer in the conference room, and I was telling him we use scaled data, and this was 10 years ago. And then you should, think about that because your design is very dense and you're using a separate board shop and a separate assembly shop. And I guarantee the board shop's not sending scaled data to the assembly shop. And the guy got really mad at me. I've never heard of this. What are you talking about? Scaled data. So it's a real thing. Our assembly division always asks for fiducials. And now we're even asking customers to add fiducials on their design, of which a lot of customers say no, but at least they, maybe the next iteration of their design, they would add a fiducial. If you can't put it on the board, put it on the rails when you design your array. How many people design their own arrays? Yeah, don't. Let the fabricator / assembler design the arrays. It's the right approach. It sounds easy, but it's really hard. I don't know why.
Do you care ODB++ versus the IPC? Which best for fabs?
ODB has a licensing thing hanging over people's head. It's not like just an open thing, and IPC is driven by a consortium. IPC 2581 is driven by an IPC consortium, and I think they're really pushing it forward. So long answer is I prefer IPC. Cadence and other tools are able to import IPC 2581 stackups, which I think is a really nice thing. I think KiCad has it on the list, or they should have it on the list to import 2581 stackups. So it's allowing for bi-directional conversation. A fabricator and assembler really tweak the designs a lot before they manufacture. And for us, we are in the practice of always asking for permission because, the boards are going into space or some military thing, or even if it's not, we always just ask for permission. But a lot of fabricators don't ask. They'll just modify your design and build it. So you really don't know what they're building. I mean, in all honesty, and especially if they're assembling too, you don't know anything. But 2581 is promoting bi-directional conversation, so you get the data back. You can import it into your CAD tool if their CAD tool supports it. You can look at the comments or changes or have like a nice discussion. There's lots of possibilities, basically. People aren't doing it as much, but yeah, short answer is go with 2581.
Yes, I like to use tin bismuth with a smidgen of silver 138C solder for prototype assemblies for ease of rework. What is your outlook on that? Is it becoming more popular, or it's dying? Or some houses will do it, some won't.
I think if you specify the solder paste that you want, the house should do it.
Okay. Thanks.
Yeah, but what's the most common, it's really up to your fabricator, because it's all about process tuning and process refinement. And if a fabricator and assembler is used to one kind of solder paste, it's because they've perfected that solder paste. So I would, it depends how much you hold that near and dear to your heart. But I would always go with what the assembler wants to use or prefers.